Okay. And we should be live. How's everyone doing? Okay. I feel happier. I don't know what it is. Just like, are people happy?
I think it's a little.
The weather?
Warmer out.
It is quite nice. It is quite nice. It's a little rainy. It's a little rainy last night, but it's quite nice. Okay, well, maybe we're also like, we can do this. We've only got a month and what, like a week about it, and then we're off to our summer obligations. Okay, so today it's session 18, and it's kind of a small add-on to what we've been doing with transformations. You know, the videos are not necessarily super short. Now, the last one is, and we have 4 problems, which is kind of the standard now for this class. But it's kind of a nice little add-on. Yeah. Oh, yes.
Are any of the homeworks going to be dropped? Like, say we missed one, or would any be dropped?
It's like the one time I don't ask if there are any administrative questions. You come right in. I wasn't planning on it, but maybe you can start a chat on the group sheet trying to convince me why that should be the case. Huh? Really consider it? Okay, well then put it in the group me and like let's see if people, because there could, and if you disagree with that idea, let me know. But I think it's how do you put it? Look, we've all got a lot going on, right? And so if someone needs to if there's an emergency that's maybe not quite an emergency that they can send me a message about or whatever. Yeah, okay, I'm open to it. If anyone's opposed to it, just let me know, okay? In a private message. But yeah, okay, fine. Let's say we'll drop 3 problems. Okay, this is a tentative thing. Okay. I had to see. Maybe it's 3. I don't know. I had to look. Yeah, because early on we have 3. No. Sorry.
I was like 17.
No. All right.
Switch it real quick.
You guys are just like I was saying, we're all cheery. Okay. So so today the session is on max min principal stresses and max shear. And this is all planar, okay, in a plane, okay? So essentially, right, what we're doing is starting, where is the thing? Here we go, right? We're starting with an element and it has some state of stress on it. We'll use a different color just because. Okay. And then we're asking questions about how much do we need to rotate it, and how much do we need to rotate it to get to a state where we have only normal stresses, okay? And that's going to be giving us what we call principal stresses. And how much do we need to rotate it to get maximum shear stress? Okay, so what you typically kind of see in these types of problems is someone saying, okay, I'm going to rotate by some amount, and now we're going to have like a sigma 1 and a sigma 2, okay, and no shear stress, all right, and we're going to specify some, there we go. Okay. Something like that, all right? We rotate to a particular orientation, and that's a transformation, and we have no resulting shear stresses, and we have kind of a maximum in-plane normal stress, right? That's one of our principal stresses. And the reason we care is that when we talk about failure, the brittle materials, they typically fail due to normal stresses. That's the mechanism behind it. And then the other thing that we look at is taking an element, maybe rotating it even more. And really, this is actually, if it's the same initial element, this is like 45, it is 45 degrees offset, okay, from the state where we have principal stresses. And we would call this, if I can put it together, okay, this one we're going to call theta S, okay, for shear, all right? And in this case, we're going to have a tau max, okay, and we will get potentially a normal stress that is the same for both sigma x prime and sigma y prime, okay, and that's the average. Right, so this thing, I mean, we're really interested in tau max, and we figure out, we show how you do that. But what's kind of interesting here is that this sigma ends up being sigma y over 2. And so in the case of pure shear, okay, the sigma x plus sigma y divided by 2 is equal to 0. Okay, so pure shear, for pure shear, okay, and I'm kind of, so this is kind of just a basic overview. There's, there are the transformation equations, there are specific equations in the notes that explain how to do this. There's a bunch of Python code. I don't expect you to write the code, but I expect you to be able to press Control Enter, for goodness sake, and see the results of what's in there, okay? That's all you have to do, all right? Hit Control Enter and it runs. Make sure you start with the import, or I guess on a Mac, what is it on Mac? Control Enter or Mac Enter? I don't know what it is. Command, that's what the thing is called. Command Enter, right? And so, essentially, a lot of these problems are give-me's. You just change the numbers, all right, that are in there for sigma x, sigma y, and tau xy, and then it spits out all the results you kind of need, okay? But choose your adventure. Choose your own adventure, okay, today. What I will say, and I'm fine with you using the equations. That's what they're for. That's what the transformation equations are for. Please, though, for exam 2, be able to draw the equilibrium on one of those slices, okay? Because it's a little hard for, obviously we're taking some shortcuts with 120 students, and we're not grading all your diagrams right now, okay? But on the exam, that's a possibility. Okay, so just make sure you know how to do that as well. Any questions? Thoughts? Oh, why do we care about maximum shear stress? Because for ductile materials, that's the mode of failure, usually. Okay, so if we can figure out what the max shear stress is, we have an idea if we're above or below the threshold for failure, for yielding. Okay, great. So let's go ahead, get rocking. I'll be going around. There are 4 questions and four portions to the video, and yeah, I hope that it's a little bit fun. Like I was saying before we started the video, the class is getting real at this point, right? It's a combination of a little bit of rigor and a little bit of conceptual mind bending for some of these questions. Okay, so yeah, let's discuss them as you work on it. Okay, cool. Yeah. Yes, there.
I can send you this. I don't know when we get the.
I know that. I didn't really focus on it, so I tried.
We're pretty close.
No, because I subbed it in.
Oh, that's what you said.
And I do I'm on exactly on track. But my next semester, I don't have to worry.
Yeah, fair enough.
Only take physics in the spring, stuff on Kubernetes. Filling out the requirements.
That's like an easier. I was gonna say, it doesn't really sound like. Even if you felt that way, it doesn't.
No.
You're not gonna dive in yet. You're gonna dive in.
Oh, okay.
Because you live by it. That's what.
Oh. I see, yeah. It's like a bump.
So do you know you're taking next semester now? Really? That's really good. Yeah, once you get the cookie dough. So when do you have it set up yet?
Well, no, I have to still apply. I was having worse on that went on.
Why don't you do that?
My next class, I'm what
Oh, okay.
econ.
I think even like next like time we had math.
There we go. Better.
Yeah, but she said she can definitely say she can.
Yeah. Social work, social.
This?
I have no reason to doubt that.
Yeah, just make sure you know everything about the company.
Or what they do.
What they do. You want to know how they make money?
So extra research on that.
Well, okay, so the big thing is,
Wait, what is the interview part? What do they ask?
well, I don't know what they're gonna do, but generally, a lot of companies do behavioral questions, some do technical questions, not all of them. You
It's
can't
a
really
technical
like.
question.
But don't. But even if you don't know, like give it your best shot. Like don't be like, oh, I don't know. Like actually, seriously try. Why? I've done it once with I've tried Red Bull before. It tastes really good.
How do you know specifically it's Sigma 1?
Because it said so.
For that question.
I was having a hard time with it. Sanderson does. Got 5 minutes. If you see what's in it.
No, I got a picture. The next. What are they doing? We didn't see it first.
To burning numbers.
15 times.
Yep.
Yeah, well, listen.
That's true.
You even get that. Or here's the next one still. Watch this. This.
Yes, he loves Jonah Hill now. He loves Jonah Hill.
No. It's a shear, it's principle. Link.
Okay, maybe I should take a couple minutes to go over this because this is pretty similar to the questions that you just asked. Okay, so if you're working, great, keep on working. Try to ignore me. I won't bother you. But if you're interested, let me take a minute to just to explain the equilibrium with transformed elements. Okay? So if we start with an element and you're like, I've seen this a bunch now. Why do you keep doing this? Because it's confusing. Okay, so there are a couple things about this element that we should note. Okay, one, it's planar, and two, we're following the conventions. All right, we're not going to a convention, we're not having a big conference, but we're following the conventions. All right, what are those conventions? Those conventions are that when sigma is coming out of a face, it's positive and it's tensile. All right. So we see that twice, here and here and here. And then the other convention is that for shear stresses, okay, it's positive when I'm on the positive face, all right? So this is the X face. Okay. Da, 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 da. And this is the Y face. All right? And so remember, X face, the first subscript is the face, the second subscript is the direction when it comes to shear stresses. So that means that I'm on the X face and I'm in the Y direction. That means it goes up. Right? This is positive Y, this is positive X. Okay, and if this, once you've got one, the rest have to follow suit. They have to follow suit. Okay? So that means that these guys, this guy has to be opposing this one, and these two down here have to be opposing each other, right? And you can go back, and that's for equilibrium. All right, so that's the first thing. Imprint in our minds that this is how we define a positive state of shear stress and a positive tensile stress in the X and a positive tensile stress in the Y direction. Okay? From there, all right, now we say I'm interested in rotating. Okay. And this is a horrible looking element. Okay, but when we rotate, okay, we are now, this is going to be our new X prime direction. This is going to be our new Y prime direction. And this is going to be our angle of rotation. Okay? Now, you're like, okay, I understand, not a biggie, all right, that this is going to be sigma X prime, right? Not a biggie, this is sigma Y prime. Not a biggie that there are other normal stresses. Also not a big deal that I have a tau X prime Y prime and tau, this is really on the Y face, okay? And it's in the minus X direction, okay? But it still has the same magnitude, okay, around. I'm sorry, what did I say? No, this is, it's on the Y face and it's in the positive X direction. Yes, sorry. So this would be like tau Y prime X prime. All right. So you're like, I understand this. Why are you doing this? Because the next thing is what I think people are getting confused about. All right. The next thing is, what if I instead decide to do a slice like that? Okay. Now I have options. I have options here. Okay. And what I suggest, right, is we draw a little triangle and we look and we see, okay, look, this is a shorter side than this one. And I should have probably made it more exaggerated. What would more exaggerated look like? I'm just going to undo this. More exaggerated is actually more vertical. Like that. Okay? This is even more exaggerated. Okay? And then it's more clear that I've got a small angle and I've got a big angle. Okay, you probably can't see that. Small angle here, big angle here. They're both less than 90 degrees, of course, right? Because this is a right triangle. So let's just say that we put the theta in the small spot. That's usually how I feel more comfortable. Okay. Now the question is, how do I relate this theta here to this theta here? Right? I think this is where people are having a little bit of funkiness in their thoughts. Well, the easiest way that I find to do that is to come down, draw a line, draw a new element, okay, like so. And this is going to have some amount of rotation. Like this, okay? And now the question is, what is this angle? Well, let's just draw it like this. There's a triangle. Is this angle corresponding to the small side or the long side? It's corresponding to the small side, right? So this theta in there is the same angle as this theta in here. Okay? And if the problem had given you the cut defined like that with an alpha, right? Then we know that our angle of rotation, and mind you, it's in the positive z direction, right? Positive z direction, this is counterclockwise, right? So this is, positive z direction, and counterclockwise, okay, it's really 90 degrees minus alpha. Okay, so now we've settled this kind of simple question of just orientation, all right? But what do we do once we know the orientation? This is where it gets a little bit tricky, all right? So we have a sigma x prime, a sigma y prime, a tau x prime, and a tau, we have sigma x prime, sigma y prime, tau x prime, y prime, okay? And we need to be able to get force balance, okay, between these new directions. So that means, okay, that for one kind of transformation or one type of correlation, I'm going to have one triangle. What do I mean? It means that for sigma x prime, I have one triangle. And for sigma y prime, I have a separate triangle. Okay, I need two triangles. I can do sigma x prime and tau x prime y prime, and I can do sigma y prime and tau x prime y prime, but I cannot do sigma x prime and sigma y prime with one triangle. I need two triangles. So what am I saying here? Well, let's take a look. If now I'm defining this as being the x prime direction, okay, and this now to be the y prime direction, okay, then what type of triangle do I need for these things to line up? Well, for the x prime, so let's say this is for sigma x prime, okay, which triangle am I going to use? I'm going to use the one that gives me a normal face in the x prime direction. Okay, that might sound like a big mouthful, but that is the following. And again, this is why I make exaggerated triangles. Okay, right? Small angle, theta still there. Okay, and where is x prime? X prime is coming out of that face. Okay? And that's pretty much, this is the big key right here. Sigma x prime is coming out of that face. X prime is coming out of that face. 90 degrees to it. I can draw tau x prime y prime. Okay? But there's nowhere to put, look at this, there's nowhere to put sigma y prime on this triangle. Nowhere. There's not a face that is parallel to y prime. I can draw, it's not, I'm sorry, that's it's not a face that's normal to y prime, okay? I can draw the y prime face, or I can try I'm saying the wrong thing. I can try out the y prime direction here, like this, okay? Which is fine, that's great. But there's no place for me to put that stinking sigma y prime, okay? So what do I have to do? For sigma y prime, I have to choose another direction, okay? And in that case, I'm going to go down here and I'm going to choose something that looks like this. I'm going to choose a triangle again exaggerated, that has theta in here like this. Okay? And now, right, look at what I've got here. I've got I didn't do a very good job because it's actually maybe too exaggerated. This face is supposed to be parallel to this face. Okay, so let me see if I can do this. Let's do this. Let's just get rid of this. Okay. This face, okay, is supposed to be parallel to that face, kind of. All right, it's a little bit of a stretch, but it's kind of. Okay, kind of like that. So now what we've got is a nice sigma y prime that can come out of here, like that. And we've got, again, okay, so now the shear stress is a little bit different, right? It's actually, so it's parallel to that face, or, okay, it may be easier. Sorry, I'm doing things kind of funkily. Okay. All right, we're gonna make it kind of parallel to this face, like that, all right? So if it's parallel to that face, right, the way I define my tau, x prime, y prime, which way? It's this way. That's the direction. Yes? Say that again? Oh, it can be labeled. That's actually a more exact label. But tau x prime y prime is equal to tau y prime x prime. Right? So your question is, why don't I label this one tau y prime x prime? I labeled it tau x prime y prime. They're the same, all right? They're the same. And it's because of equilibrium, actually, just general equilibrium. If you go all the way back to this element, right, it's exactly what we're saying. This one is the tau xy. This is actually tau yx. But because of equilibrium, their magnitudes are the same. And we have to be very careful with their directions. Okay? And I guess this is that theta again. And again, because I've drawn exaggerated triangles, I know that that's the small angle. Right? I know that's a small one. Okay, so that's the first part. Maybe I should go, I don't know, should I go one step further? I should probably go one step further, okay? Because we've gone this far. It's sad if we don't, all right? Okay, maybe not that sad. Okay, maybe only for some of you. Okay, maybe for, anyway. If I come over here, right, this is the original sigma x. If I come over here, this is the original sigma y. Okay. So now I've got a problem. I want to do equilibrium on this triangle, but I can't do equilibrium when sigma x and sigma x prime are not parallel to each other. They're not acting in the same direction. I can't do equilibrium with sigma x and tau x prime y prime because, again, they're not in the same direction, right? So we have to get them acting in the same direction. And then on faces of this triangle. So the way we have two things to keep in mind. Okay, normally we talk about the size first, but let's just talk about the vectors associated with these stresses first. Okay, so here, in order for us to get components that are in line with what we desire, okay, we have to break the sigma x and the sigma y into appropriate components. And this is where we go back to, like, I don't know, high school physics, right? Where we said, hey, a vector can be broken into multiple components, and I can add these vectors together to get the resultant, right? So here, what we say is, I can come up with, and I'm sorry, I'm not trying to make this simple because I screw this up all the time, right? But those are the two components. And you see what just happened there? This side of this vector, all right, is now parallel to the x prime direction. This side of this vector is now parallel to the y prime direction. Okay? And so this allows us to do some superposition and some addition, vector addition. And it's very important to also know which direction these components are going, right? So this vector, if I want to add, right, it's head to tail, or tail to head, however you want to put it, right? This is, right, those two are in that direction to get that resultant vector. And these two right down here are going to be in these directions to get that resultant vector. Okay? And because everything's exaggerated, I don't have a problem putting theta in right here and right there. Okay? Because I know that that's the smaller angle. I decided my thetas are going to be the smaller ones. Okay? So then when it comes now, right, I know that this one is going to be sigma x times sine theta, right? So this side is, actually I'm going to undo that. Just because it's big, I'll use this one. Sigma x sine theta over here. This side is sigma x cosine theta over here. This side is sigma y cosine theta. This side is sigma y sine theta. Okay? What's left? Two things. What are left? One is we should probably name these sides. Okay, so this side is the delta A cosine face. This is the delta A face, and this is the delta A sine theta face. So after we've done all this, equilibrium is kind of easy. The hard part is getting these triangles set up. Okay? Equilibrium, that's the algebra, right? That's why everyone looks at the solutions to the exams and says, this is super easy. Yeah, because it's addition and subtraction and division and multiplication for the most part, right? It's the drawings that are the pain and in our necks. All right, so yeah, let's just do one because I don't want to keep you from your homework, right? But if we do the summation of the forces in the x prime direction, right? The only big time stress that's acting in that direction that we care about directly is the sigma x prime, because tau x prime y prime is orthogonal. So that would be what we'd solve for the forces, summation of the forces in the y prime direction. So in that case, right, in this case, we can say that we have sigma x prime delta A, right? And then we have that, and that's in that direction. We have a sigma x cosine theta in the minus direction. So we're going to do sigma minus sigma x cosine theta, and its times is acting on the delta A cosine theta face. All right, and here we have a minus. Okay, we have a minus sigma okay, on the delta sign. And then you guys tell me, what did I forget? What did you forget, you silly guy? Yeah, we're missing some shear stresses, right? So this is a big time bummer and a big time pain, right? But we need to draw two more shear stresses. And which direction do they go? They go in these directions, okay? These are shear stresses on these two faces. So we have a tau xy in that direction, and we have a tau xy in that direction. Okay? And we also have components, all right, of them, all right? So we have this component like this, and we have, it's hard to do, right? This is what I was talking about. We have a long component and a short component like that, okay? So what do we do? Well, this tau xy, all right, the component that I'm interested in is this component right here, the one that is acting parallel to sigma x prime, okay, and it's going negative again, all right, so it's going against that direction, as everything has been so far, okay, so it's going to be minus, and which one is that? That's going to be a sine theta, okay, so it's going to be, again, minus tau xy sine theta times the delta A cosine theta, right? And then this one over here, okay, is going in that direction, is also against sigma x prime, all right? So, and it's this face right here, okay, and that's going to be an adjacent face. That's a cosine. So we're going to have a minus tau xy cosine theta, and that's on the delta A sine theta face. And now everything's equal to 0. Okay. I might have made a mistake here because I was just doing this on the fly. Okay, but that is how you go about figuring out how to map a slice at a given angle, okay, with a counterclockwise based rotation. It could be a clockwise, and if it's clockwise rotation, then it's negative of a counterclockwise rotation, right? And being able to then do equilibrium on the diagram. Okay, good. All right, go back to whatever you were doing. Yeah, go to 4. Yeah, so yeah, for as long as you have linear elastic material, yes. It's younger because right, we're not saying
Oh yeah, so yeah, the team next.
See? Minus A. Right, all those values. Every orientation has its own set of like X and Y values. Right? So those are all.
two don't. Do you disagree? Might be my equations or Canvas, but they're not working.
Yeah.
What's up?
Question two for the finding the max. I think it was the shear in plane.
Mm-hmm.
I did it both on Desmos and on the Colab like you did. I have the same answers, but it just says it's wrong.
Well, let's the rotation angle, right, that we need is what we're trying to find out, right? And what is the initial state of stress? Where is it right now? Sigma x is equal to 50. Sigma y is equal to minus 10. Okay, and tau xy is 10. All right, so we have, okay.
And then, yeah, I did that before.
Oh, did I put in the wrong expression? So in Colab, which one is it? It's the, so in the notes, what do I have? What do I write in the notes?
It was 450.
Okay, and what did I write in Canvas?
It was 15 milligrams.
Okay, so let me just add another 0. Okay, sorry about that. So I forgot a 0 when I put it into Canvas,
Okay.
which is making a difference, of course. Wait a second, what did I? Yeah. Sorry guys, yeah. Okay. Wait a second. So then, yeah, because my answers. Yeah. So this no. That's example 18.1. Example. What did I do? Go. Wrong.
I was watching the video. So I'm gonna show you how to do it.
Oh, wait a second. This is two-way? Yeah, I put this in wrong. Completely wrong, right? Yeah. No, this is, yeah, it should be minus 100 and that's why. Okay. Put this in completely wrong.
This is a different question.
I apologize. Let's fix these. Well, thank you guys for your patience. Thank you everyone for your patience. It was meant to be a simple problem. The problem is that this time I finished the problem set at about 3 a.m. I don't know if you guys ever have any problems at 3 a.m. with your cognitive abilities, but I do. So my apologies.
You write these at 3 a.m.
Huh?
You write these at 3 a.m.
This time, sometimes I pick my poisons, right? So like, do I want to finish the video at 3 a.m. or do I want to finish the problems at 3 a.m.? So last week I finished the videos like at 3 a.m. So if you ever see the videos I'm like falling asleep, it's because it's very late.
How long do you sleep?
Normally much more than this semester. This semester has been, for you all, this class, as much as you may not appreciate it, this class has taken me a lot of time.
Well, thank you for your effort.
Yes. Yeah, all right.
Hopefully you can just reuse the videos.
I
next
love
semester.
this class.
Yeah, we're too.
So, and then as an announcement, I do. No, that's the point. That's part of the point. Is that we're going to. This is how, with your feedback and everything, and which I hope you provide. Especially if you have new videos or things that are on the internet that you want people to watch, let me know because I can put them on. But yeah, the point is to keep evolving this so that we have like a flipped classroom.
How many times have you taught this class?
This is my 5th time, so this is the first time we flipped it.
What made you want to flip it?
I've been interested in trying to make content that is usable for classes, not just ours, but across the world, and having living content. Right. So I'm not saying that people will adopt this, but the idea is that to make something that's kind of not branded, right? That people can just kind of plug and play. And then focus more on the in-person interactions, and essentially changing this role from lecturer to consultant. That's the vision. That's the vision, everybody. And then I guess as another kind of announcement, if you know anybody who wants to take this class this summer, guess who they get to take it with?
Oh, shit.
Guess what?
Yeah.
I can almost guarantee.
Maybe I'll get to see you again over the summer.
No, I don't think I'll see you all this summer. I better not.
Oh, God.
If I fail this time, right, can I write the exam over summer? I'll help you out.
Yeah, you can be the chief.
I'll be like a TA, yeah. Just unofficial,
If you take it, again, if you were, you'll find that it's very similar. You all are helping us work out the bugs on the questions. Huh?
I love seeing you that.
You like being on that? It's good times, yes. Mhm. you're fine. As long as you got the points, right? You're fine. But yes, the numbers are now different.
Well, because
The numbers are now
I
different.
watched like all of it.
Yes.
Data consumed, yeah, just-
Yeah, you can say, or you can say beta p plus 45 degrees. Beta s, yeah.
At data S. Sigma.
What are you doing?
Oh, it's the same thing. Always. Yep, you got it.
Same thing as the first question. Same question. Yeah. Yeah.
Same case you
It's the same question. I don't know if we all understand.
Good
For
work.
which one?
That's our workout of the day.
For 18Q.
18.2, you should have all the same questions, all the same numbers. Yeah, okay, now you all know. Yes, yes. good
Not
question.
that I would ever cheat.
No,
Yeah,
but
I love
it's
academic
actually,
integrity.
I
Yeah.
mean, the yes, the problem, as you just saw, the problem is actually simpler, because it's just 100 minus 1, 0. But I have not changed it to be that. The slides are right. Yeah, and also the next time I teach this class, I anticipate we'll have a lot more time to answer questions on the group meet. But the group meet gets bonkers the night before. And I just can't. not when I'm trying to get the all the content together. So hopefully once the content's all kind of laid out, then I can be up. Then I'll only be up to like 10:30 p.m. though, but I still be able to answer up to 10:30. And then when like Apu's sending stuff at like 2 a.m. saying like it doesn't look, I can't see anymore, everything's really fuzzy. No, I mean, I'll be honest, I make a lot of careless mistakes. Like that is my thing. And that's one of the things I like about college, is that on the exams, they, they could tell, they would reward understanding. Like, it's like, oh, you made a little mathematical error, right? It's like, it wasn't like all or nothing.
You didn't go to Rutgers, did you?
I didn't go to Rutgers. Sorry, if some of your classes are all or nothing, I respect that.
During COVID for Calc 1, because it was all online.
Oh yeah,
Oh, it was
yeah,
awful.
yeah.
It was bad.
It was hard. It was hard. Yeah, that fall of 2020 semester was really brutal.
For us, like, that was, I almost failed my class just based off the exams, because I kept getting assigned errors.
But also, I can't really say that I never mess up on the concepts either. It's not everything I do wrong is not because it's a careless mistake. Yeah, and the other thing that I want with this class is not to, like, it's not supposed to be, like, branded. So, like, we want to use the best content that's available on the internet to reinforce the concepts. So it's like, I'm okay if you guys don't watch these videos. That's fine. But we're trying to find the ones that are really good.
I do prefer watching the videos just because that's what's related to what our
Yeah.
assignments are.
Well, yeah, that's kind of new. But I'm not nearly as entertaining as some of the other people out there. So
I mean,
that's fine.
like for me, like how entertaining is mech materials going to get? Like, I mean, respectfully.
Well, that would be one thing that I would like to do in the future too, is they kind of have a bunch of experiments that you could do with household items, and have like some more demonstrations, right? So it's like you see everybody with a pool noodle, right? That pool noodle keeps coming up on all these all these videos. Like I should probably buy a pool noodle, right? But I haven't bought one.
When you did with the risk crap, it was pretty helpful.
The Ritz cracker? Okay. It was, you internalized it.
Yeah.
You internalized it very well, didn't you?
Right now, yeah.
Good things. I have to keep that in mind. So there's this professor at he's now passed, but he was you guys have probably heard of this company called Bose, right? So yeah, the headphone company, right? And speakers, right? So Bose was a professor in electrical engineering and computer science at MIT. And I never took one of his classes, but one of the people that would take his exams, apparently he would bring a bunch of ice cream to the exams, and they'd give him as much time as they wanted for the exam. So there was no time limit, and there was ice cream. And my friend told me, you've never seen such a sad, sorry-looking group of people eating ice cream together. Because they're not allowed to talk, right? They're not allowed to talk about what's going on. And it was like eating the ice cream on an exam that has no time limit, right? That's kind of interesting. Now, I don't know if that's true. Maybe someone who knows Bose better can, clarify if this is really true. But this is what I was told.
Well, would the ice cream have been like incentive just to get it done faster so that it didn't melt?
So maybe, right?
Like, that's what I would think.
Yeah, you only have so much time before the ice cream melts. I
Yeah.
don't know. So,
Yeah. Ice cream
Once the
melts
ice
are
cream's
done.
gonna be done.
all right. Any other questions? I might close the go ahead and close the live stream because we're getting on topics that are a little bit off of what we're doing here. But it's been fun.